Okay, here we go. So sorry about that. I just had to find the record button. Right. Okay, so we ended off with talking about, we were looking at energy diagrams. And so just in the last reaction, we had two products that were combining with each other to form two new products. One was a leaving group, one was either the elimination product or the addition product. And so with our energy diagrams, there's actually, with many reactions, particularly the elimination reaction, which we did a second ago. Like if you've got a product which looks like this, starting material, I should say, and we're using some base, and it's going to grab a proton. You notice that there's protons on this carbon and there's protons on this carbon. So there's two potential products that you could actually form in this reaction. One would be a double bond on the end. The other one would be a double bond in the middle. And so often, one of these two processes will be lower in energy here and generate products that are thermodynamically not as stable as E and F, because the lower you are on this diagram, the more thermodynamically stable you happen to be. So there's basically, and the lower the activation energy is, the faster the reaction will be. So you don't need as much energy to overcome this barrier, and so these products will form faster, whereas you need more energy to overcome this barrier, but these products here are more stable. So we call these kinetic products and thermodynamic products. So kinetic products have a lower activation energy, EA or delta G dagger. So they'll form faster, and thermodynamic products, their delta G naught is lower, so they'll be more stable. So this isn't always the case for all reactions, but in certain reactions, it is certainly the case. And this is a little example of one of them, which when we get to the elimination section, we'll see that this product is more stable. This product could form faster. That's basically where we're gonna go later on. Let me clear these diagrams. Now, at other times, you don't just start with products, start with starting materials and end with products. Sometimes you make something in between. And so there, on an energy diagram, there can be peaks like this bump and this bump, and there can be valleys like this little plateau here. And so the peaks are what we call transition state. So this is the energy we have to overcome to get to this intermediate. And then these valleys in the top, I guess I just gave that away, those are what we call intermediate. So this could be maybe a carbon that's like a carbocation, something which is missing a substituent somewhere, and then when it forms its substituent, it's the final product over here. So all of the valleys on energy diagrams are what we call intermediates, and all of the peaks are transition states. So intermediates can sometimes be isolated, or sometimes they can be isolated. Sometimes they can't, depending upon how reactive they are. Transition states can never be isolated. You basically have to determine the transition state through different types of spectroscopy sort of techniques. So physical chemists like to use lasers are a good one for some of for techniques of how bonds are breaking and that sort of thing. So as laser technology has gotten better, deducing what's actually going on in these transition states has gotten far better. There's also computational methods which can be useful in predicting what a transition state would look like. And as basically computing power is increased, the modeling has become more and more accurate for these types of things. So the key point is that a peak or a transition state can't be isolated, but you can sort of figure out what it is based upon the intermediate, which sometimes can be isolated. So it's at these points where the bonds are being broken and formed. So you can have half a bond, like one bond's breaking while one bond's forming, that type of stuff. So this is where the bond breaking and bond making is taking place. So I guess the key point is that a peak on an energy diagram is a transition state, a valley will be an intermediate. And often, because intermediates, like if you had, for example, you can have, like we're talking about carbon here. So let's pretend that we've got a carbon which is a carbocation. Let's say this is an intermediate in a reaction. Or let's say that carbon with some lone pairs is an intermediate in our reaction. If I was to say to you, if you're comparing carbon with only 3 bonds and no electrons to carbon with 4 bonds, which one of these two do you think would be carbon with 4 sigma bonds versus carbon with 3 sigma bonds and an empty orbital? Which of these two do you think would be higher in energy? Right, the carbocation. Why? Why would this one be higher in energy? Yeah, so why would this guy be higher in energy? That is absolutely correct. Right, it doesn't have its octet isn't filled. It's missing some electrons. It would like 4 bonds, so it's going to be higher in energy, right? So often when we're seeing these energy diagrams, the intermediate's actually higher in energy than the starting material. And here's another example. If we have a carbocation, so carbon with lone pairs, which means this is carbon with a negative charge. If we're comparing that to carbon with 4 bonds, which one do you think would be higher in energy? Right, the carbon with the lone pairs. Because remember, carbon is an electronegative. It doesn't want a negative charge. It would prefer to be just have 4 sigma bonds and have all of those electrons shared equally with whatever it's bonded to. So intermediates are often higher in energy for our little processes which are going on. Now, it's true, you could have I can't think of an example, but I can't think of an example of, maybe in some biochemical process when you're using an enzyme, an intermediate might be lower, but it'd have to be going down. But I can't think of one in chemistry, in all honesty. So often the intermediates are higher in energy before they become lower in energy, if it's a endergonic process. This could go to here, and then it could go way up to here for a non-spontaneous process. But so, yeah, so transition states, the peaks can't be isolated, valleys, intermediates sometimes can. So let's erase this drawings. Okay. So let's go to the next slide. Right. Okay, so there is something in organic chemists and physical chemists have, because we can't isolate a transition state, what people have done is use a postulate which basically describes that, okay, we don't know what a transition state looks like, so what we're going to do is we're going to compare it to something we do know what it looks like on the energy diagram. It could be starting material and a product. It could be starting material and, say, an intermediate. And so in this process here, we've got methyl bromide and some nucleophile, I guess it's a chlorine atom, is coming in and it is attacking the carbon, and the bromine bond is breaking, and we're making methyl chloride. And so at the peak of this transition state, we would use the Hammett postulate to describe, okay, is it closer to a starting material or is it closer to a product? Some transition states would be exactly in the middle. Some are closer to one than the other. This example happens to be one which is closer to, which is right in the middle. So carbon can't have 5 bonds. And so basically what this is trying to show, the transition state which is proposed, is that the chlorine and the bromine are equal distance to the carbon, and this bond is starting to form and this bond is starting to break. When you get to point B, because it's getting closer to our product, this bond is shorter. It still hasn't formed completely, and this bond is longer because it hasn't completely broken. If I was to draw a diagram here, we'll call this point C, or point Z, I guess. Let's call it Z. What this part of the transition state would look like would be if the carbon and the bromine, this bond is starting to break, but this is short, and the chlorine is starting to approach. So this is long, and then the rest is sort of, no, let me erase this a little bit. So this part's long, dagger. This part's short, because this bond it's still far away. So we were saying that the transitions, this little, whoops, where's my spotlight? This is closer to this structure. B would be closer to this structure, but they're not those structures yet because they haven't reached this point of the energy diagram. And point A would be right in the middle. So this distance would be equal to that distance. So the Hammett postulate is basically saying that you choose the two, either the starting material and the intermediate, or the intermediate and the product, and you base the transition state structure off of which one it's closer to. So in this case here, it's right in the middle. And so it's something which doesn't look like anything. Like it's a trigonal bipyramidal structure where these bonds haven't fully formed or broken yet. And as you're getting closer to this product here, you see that this is starting to become a tetrahedron, just like this would be, because this carbon here would be tetrahedral. Here, where this chlorine's coming into attack at Z, it's starting out as still almost like a tetrahedron. This bond is starting to break, this bond is starting to form. So that's basically, Hammett's postulate says that if you can't see what the transition state structure is, you look and see, is it closer in energy to starting material or product, and base it off of that. And sometimes it's just right in the middle. So this reaction is what we're going to talk about next, which is an SN2 reaction. And the transition state structure is right in the middle, and it's basically a trigonal bipyramidal structure because carbon can't have 5 bonds. This bond's starting to be formed, and this one's starting to break. But there are other examples where sometimes it will be closer to one or the other. So if you've got a system where you've got your starting materials over here and your products here, and this transition state is closer to the starting materials, so it's an exergonic process. Let me erase this, clear all drawings. In a case like this, we would say that this is an early transition state because it more closely resembles starting materials. If you've got an endergonic process, so here's your starting materials and here's your products, the transition state is closer to the products, so its structure would be closer to the products. And we call these late transition states. And then the one in the middle is just, there is no particular name for that. So the previous example is neither early or late. So in a process where you're going uphill, this first transition state should be, or this transition state here should be a late transition state. And if you're going downhill, this should be a exergonic. This transition state should be early compared to that. Right, so I think there's a little example here, the next page. Right, so this diagram's basically got it all. So we've got and this is an example we did in class a bit earlier. When we were talking about electrophiles and nucleophiles. So we had a double bond, and it was the nucleophile, and we had HBr, and this was the electrophile. Remember, this bond, bromine is polarizable, so this H is delta plus. Remember, HBr is one of the strongest acids there are. So this molecule is the nucleophile. It attacks the proton. These electrons move on to the bromine. And the nucleophile becomes the electrophile in the second step. It's a carbocation. You've got your bromide. Negative goes to positive, and you make your bond, your carbon-bromine bond. And so this overall is an addition reaction. It's an electrophilic addition reaction because we're adding H and Br to the two carbons of the double bond. H gets added first, then the bromine. So in our energy diagram here, this intermediate, this will be an intermediate. This carbocation will be an intermediate. So just as we did last time, because this is missing some electrons, this will be higher in energy than our starting material. So it's going to have to go over through some transition state to where this intermediate. And then the next step is the bromine comes in and attacks, and it'll go over another transition state, and it'll form our products. So overall, this process is, it's got a negative delta G, so it's spontaneous, but there is this intermediate we have to form first to go down to here. So there's essentially two activation energies. One's larger than the other one, two transition states. And if we were to look at this transition state and ask ourselves, should this be an early transition state or should this be a late transition state? So we're comparing our starting material here to our intermediate here. So should this be early or late? This transition state, is it closer to starting material or intermediate? Late, right. So this should be late. It should be a late transition state. And so, right, so this is going to closely resemble carbocation. So this transition state, it's going to have some carbocation sort of characteristic to it. So we're making a bond between this carbon and this proton, so it might look like we're forming this carbon-hydrogen bond, and this carbon is developing a positive charge, because over here it's got a positive charge. And this is going to actually, later on when we do these reactions, it's going to tell us something about why reactions proceed the way they do. Okay, and so in the second step, we've got this carbocation, and we're going to our final product. Should this transition state be early or late? Does this closely resemble intermediate or product? It should be early, right? So this will be an early transition state. So the overall process is the first transition state's late, and it's going to resemble carbocation, and the second transition state's early, and it will resemble carbocation as well, because this is closer to that than this being to that. So that's basically how the Hammett postulate works. Every time we use it, we'll be drawing an energy diagram anyway, so it's going to become second nature, I think. Okay, what's next? Any questions so far? Okay, so there's a question is, how do you determine which is the highest energy for the rate determining step? Oh, I didn't even talk about the rate determining step. Okay, so the rate determining step is basically the peak with the highest activation energy here. Okay, right, I will go over that too. So how do you determine which one's which? Yeah, without any data, it becomes really difficult. So like if you're just looking at a reaction, with a bit of experience, you might be able to say, okay, this is the way it should be. Actually, let's see, what's the best way to describe this? Okay, a potential question I could ask on a test would be, draw an energy diagram which fits all of the following criteria. So, like I could say, what would be the following criteria? There is one intermediate. The overall process is endergonic. And the rate determining step is the second step. And so we would have to draw an energy diagram which basically fits, so there's one intermediate, which would fit all of these criteria. And so let's do that. So if we were to draw our little diagram over here, let's put our starting material really low, because if it's endergonic, the overall process, the final product has to be higher in energy, right? So this delta G dagger, or sorry, delta G naught has to be positive. It's got to be positive delta G. This would be free energy. This would be the reaction coordinate. Okay, so there's one intermediate, and we'll put the intermediate somewhere here. And then our rate determining step is the second step. So that means that the intermediate here would have to be higher than the intermediate here. So it would be something like this. And this energy diagram would basically fit all of these criteria. If we wanted it to be, if I'd say the rate determining step is the first step, then we would need to change this so that this energy diagram is here, this activation energy is here, and I'd make this a little bit lower so it was like this. So that's basically, that's one question that could be asked of how, like just drawing an energy diagram which fits certain criteria. Now, how do we know which transition state is the rate determining step? So in a reaction like this, if we were doing this reaction specifically, there is a way to figure this out sort of just by looking at the intermediates. And let's pretend there isn't any arrows here. So we've got our starting materials, should be over here. We got this intermediate and this final product. If you were to say to yourself, okay, the most unstable species out of all of these has got to be this carbocation, right? So forming this has to take quite a bit of energy. So we would expect that this energy, that this peak would be quite high to form this unstable product. And from here, we're going to something which is, all the bonds are filled. This would be a really, this molecule would be happy to have all its bonds formed. So having a bromide attack this should be a relatively quick process. So because this is so unstable, forming it's got to take a lot of work, but it reacting with something should be quite quick. So for that reason, this reaction should be quite fast. So this transition state should be a bit lower. But this sort of analysis will come with a bit of experience. But I guess the key point is that being able to draw something like this could be useful just for a conceptual sort of thing. Does that answer the first question? Okay, good. Now the second question was going over the early and late again. Okay, so let's stay on this page for a second because I think this makes sense. Okay, so for late transition states, they tend to be uphill reactions. So we're going from something which is stable to something which is not particularly stable. So an endergonic process. So what the Hammett postulate basically is saying is that we don't know what the structure of this looks like because we can't isolate a transition state. So we have to compare it to either the product or the starting material. And so with reactions that are going uphill, the species that is closest to the transition state, in this case happens to be this intermediate. So because this is closer to here than it is to here, it's late in the reaction, so we would call this a late transition state. If you're starting from this intermediate and you're going to this product and it's a downhill reaction, so the bromide's going to come in and attack here really quickly. And so this transition state is closer to this intermediate than it is to this product, so we would call this an early transition state. And then there's the previous example where it's right in the middle. We don't have a name for that. So with that trigonal bipyramidal structure that we had here, it's right in the middle because this doesn't resemble product and it doesn't resemble starting material. So this is just, it's neither. But for the two examples here, both of these would resemble carbocation in some way. Like in one case, the bromide would be approaching here, and in the other case, you'd be forming the carbocation here as this bond is being used to make that. So yeah, it's basically the best way I can describe it. I don't know if that's a good way of describing it. I think I've got a question next. Okay, let's make this big. Add timer. So here's an energy diagram with a bunch of different things on it. And the goal is to label things. So what's A, what's B, what's E, F, and H? E, F, and H. few more seconds. All right, let's see how everybody did. A, free energy. B, reaction coordinates. E would be our reactants, F products, H intermediate. Correct. So that is right. So A is free energy. It's not energy or just enthalpy. Free energy basically includes all the entropy part of the stuff. So the majority of our energy diagrams will always be drawing will be free energy. Reaction coordinate. So this is basically the progression of the reaction. Reactants are E, products are F, H is our intermediate. Excellent. Okay, let's go to the next one. So it's the same energy diagram here. And this time what we're doing is we've got early and late transition states. We've got a endergonic process and the exergonic process. Okay, let's see what everybody put. Okay, so it's basically it's basically the 24, 25, 25, 24, 24. These three questions seem to be the most, there was the highest agreement on these ones here. Okay, so, right, so early and late transition states. So transition states are either gonna be G or I because the peak is going to be a transition state. Okay, so then when it comes to formation of or endergonic or exergonic process, it's going to be the formation of something. So which would either be we're either forming in the intermediate or we're forming our final product. The D and J would be activation energies here, and C would be our delta our overall delta minus or delta naught. Okay, so for the transition states G and I, on this energy diagram, G is closer to H than it is to E, both in energy and basically in distance. So this is closer to H in energy, and in reaction progression. So G is closer to H. So we are going uphill here, and it's closer to H. So this should be a late transition state. Whereas with I is closer to H again, as opposed to F. And so this will be an early transition state because this is closer to this. And this is, if we're looking at this process in isolation, this is the start. So this is early. And if we're looking at the process from E to H in isolation, this happens later. So G should be a late transition state. I should be an early transition state. This process going from E to H, that's uphill. So that will be endergonic. And going from H to F, this will be a exergonic process. So that's basically the four of them. I wonder what the majority of for this one was. I don't have any way to check that, so I don't know. But anyway, that's how this works. So the transition states will be G or I. And yeah, so this process going from here to here, that's uphill, so that's endergonic. And actually going from E to F or H or overall E to F, those are all endergonic. So okay, next thing, substitution reactions. Where are we here? So we got a little bit of time to start substitution reactions. So the next section is basically, the first thing we're going to do is substitution reactions, then we're going to do elimination reactions. And all of these reactions are going to involve a similar starting materials. And the key point is that it's going to be on sp3 hybridized carbons. So I'll just put an X here as a preview of what we're going to be doing. So the key point here is that this carbon has to be sp3. None of these reactions are going to work with sp2 hybridized carbons, whether it's a double bond or an aromatic ring. It's not going to take place under these circumstances. So it's this little carbon here has to be sp3. So yeah, that's the key point. And so the trick for the substitution versus elimination reactions is our starting materials are going to look very similar. We're going to have X, remember, is basically a halide. So we're going to have alkyl halides as one component. And in the second component, we're either going to have a nucleophile or we're going to have a base. And so nucleophiles are going to give substitution reactions. Bases are going to give elimination reactions. And what we learned when we were doing describing what a nucleophile was compared to a base is that nucleophiles have lone pairs just like bases do. So nucleophiles could be broadly classified as Lewis bases. And of course, a base could be classified as Lewis base. So it becomes kind of, we're gonna have to do some sort of analysis to figure out what's going on. But as things go on, it'll hopefully become clear as to what's what. I don't want to get ahead of myself and scare everybody though. So that's basically what's going to be coming down the pipe here. So in the substitution reaction, where's my little laser? We're going to have a nucleophile. We're going to have our alkyl chloride. And so remember, this carbon is going to have a delta plus. So this nucleophile is going to come in and attack this carbon. And our halogen is going to be leaving. So this halogen which leaves is going to be called the leaving group. And we're going to have some nucleophile, and our electrophile will be our alkyl halide. And then we'll have a product, a substitution product along the way. And I guess as a general sort of way that these things sort of work. So we've got a reaction arrow, which is telling us what's going on. Often what's put underneath the arrow is a solvent. The reagents and are typically put on top, and what's put below is usually the solvent, sometimes a temperature, if a temperature is important, or even a catalyst, something which isn't really used, which is used to catalyze reaction but isn't consumed. So the things that could go below the arrow are like solvents, temperatures, catalysts. Reagents go above the arrow. So in an elimination reaction, it's the same start alkyl halide, the same electrophile. The only difference is this is now a base, not a nucleophile, and we're removing a proton on a carbon next door. So rather than attacking this carbon, a base is going to remove a proton, and you're going to get your elimination product. So a double bond, you still have a leaving group, and then your base is going to be protonated. So it's going to form the conjugate acid. Whereas in a substitution reaction, the nucleophile is now bonded to the carbon, but we still have a leaving group. So these are the two broad reactions that we're going to be doing. Now there's two types of substitution reactions that we're going to look at, and there's two types of elimination reactions we're going to look at. And both of these mirror one another very nicely, so it'll all be fun. So there's a question about, are bases always in elimination reactions and not substitution reactions? Yes. So what we're going to see is that a base is going to remove a proton, whereas a nucleophile is going to attack a nucleus. Now, some species can behave as both. And so what we're going to need to do there is basically an analysis of the rest of the reaction conditions to determine how it will behave. And there's basically I'll provide everyone with a sort of like a decision matrix about yes, no, and it's going to lead you down a path to either a substitution product or elimination product. But yes, so for this, bases will remove protons, nucleophiles will attack the nuclei. Someone else had a question. All right, okay, so substitution reactions. So here, the first thing we're going to need to look at is basically the mechanism of how this reaction works. So if this is our overall reaction, two things are taking place. One is that we're breaking the carbon halogen bond, or X bond in this case. The other thing is that we're making a nucleophile carbon bond. So we're making a bond here, and we're breaking this bond here. So we're breaking the carbon X bond. So remember, carbon's the electrophile here. And we are making a nucleophile carbon bond. Let me move this out of the way. And so depending upon the order in how these bonds are being broken and made, we're going to have two different mechanisms. Okay. So there are basically two options. One option is that we can break the carbon X bond and we can form the carbon nucleophile bond at the same time. So remember, when bonds are being formed or made at the same time, we call this a concerted process. So carbon X bond can break as carbon, this should have an N, excuse me, a U there, nucleophile. So these can take place at the same time, a concerted reaction, or we could break the carbon X bond first, then make the carbon nucleophile bond. Why can't we make the carbon nucleophile bond first, then break the carbon X bond? The answer is right. You can't do this. Say we've got X, H, H. Then do that. We can't do this because carbon can't have 5 bonds, right? So that you can't break the octet rule. So this third one's basically impossible because of the octet rule. So you either have to break this, X first to make a carbocation, or you need to have the nucleophile come in and attack as this one's breaking. So a concerted process. So it's either going to be 1 or 2, but it can't be 3. Excellent. Okay, good. So what we're going to see is that these two things have got very different energy diagrams, and they're going to take place under different types of reaction conditions. Okay, so good. So we'll do the SN2 reaction first. So yeah, so we're going to talk about SN2 and SN1. So SN2. So this basically is standing for, what this means is substitution nucleophilic, 2 for bimolecular. So this relies on the nucleophile hitting the electrophile, so our alkyl halide, to cause the reaction to take place. So as the nucleophile hits this carbon and starts to form this bond, the X group, the leaving group, starts to leave. So it's a one-step mechanism, and it relies on these two guys, these two molecules hitting each other it turns out with a specific orientation. So the nucleophile has to hit the electrophile. So this bond forms as this bond breaks. So it's taking place at the same time. So this is a concerted reaction. So the rate of this reaction is dependent upon some rate constant, which we would determine experimentally, and both the nucleophile and the electrophile, the nucleophile and the alkyl halide. So it's dependent on both, because this has to hit this for the reaction to take place. So that's why it's a bimolecular reaction. So I've got bio. I think I've got to just be bimolecular. So I have to go back in and change that. Anyway, yeah, that's basically it. So it's relying on both of these for the reaction to take place. And so this is interesting. So we'll get to the energy diagram in a second. So nucleophile has to hit carbon, leaving group leaves. And so there's basically two options of how so remember before I said that there was a number of different things which would affect the activation energy for an energy diagram. So for a reaction to take place, molecules have to hit each other if it's a bimolecular reaction. And sometimes there are other things that can cause the reaction to be fast or slow. And one of them is that it has to hit with the correct orientation. So is there, in this mechanism, it's concerted, is there an orientation where the two molecules must collide? And the answer is actually yes. So we can visualize this. There's two possible ways of looking at this. So the nucleophile could come in and attack the carbon on the opposite side of the leaving group, and it could leave. Or the nucleophile could come in and attack the carbon on the same side as the nucleophile, as the leaving group, and it could leave. I think intuitively, we would say to ourselves, I know which one is taking place, but we have to prove this sort of experimentally, right? So one of the interesting things is the reason why I've colored this with different colored balls here. So remember, carbon can have 4 different substituents. If this nucleophile comes in and attacks on the opposite side and this leaving group leaves, this would be our structure. If the nucleophile attacked on the same side as the leaving group, we would have this. So in one case, when it attacks from the opposite side, we get an inversion of this carbon. So it's almost like a umbrella in the wind. So it flops, goes from it's protecting you, it's concave around your head, to when the wind takes it, it's concave towards the rest of the universe. Or in the other case, there is no inversion. But if you look at this molecule here and this molecule here, what is the relationship between the two of them if all of these 4 groups are different? So we have to think back to our stereochemistry sort of chapter. That is right. They are enantiomers. So if the nucleophile attacks on the opposite side, or if the nucleophile attacks on the same side, it's going to produce different enantiomers. So one of the ways that this was proven experimentally of how it takes place is that they did these reactions on chiral carbons and found out, did they have a retention of configuration or did they get an inversion of configuration? And that would dictate what type of mechanism was taking place. So intuitively, if I was to say to you, which one do you think it would go by? Option A or option B? What would you say? I should have done a poll for this. The majority of the people who have responded have said A. And yes, turns out A is exactly the way it works. Okay, so it's a bit crowded where if this is coming this, the way I always view it is it's a bit crowded if it's coming this way to make this bond break. They'd both be on the same side. Here they'd be on opposite sides of one another. And it turns out that if you look at, if you look back at the very start of the term, okay, if you want to break a bond, you need to put electron density where? And think of a molecular orbital diagram. Right, the antibonding orbital. So if you want to break a carbon halogen bond, a sigma bond here, you need to put electron density in the antibonding, the sigma star CX orbital. So that's where you've got to put the put the electron density. Good. Okay, so now the question is, where in the world is that sigma star orbital? Turns out, if this is the if this is your CX bond here, so you got your overlap, turns out the antibonding orbital is on the opposite side of the carbon. So if you want to break this carbon X bond, you've got to put electron density into this orbital, which its location is on the opposite side of where this leaving group is. So the nucleophile has to attack this carbon from the opposite side of the leaving group. So that's where the antibonding orbital. So intuitively, we should get, most people said it should be on the opposite side, and that's indeed the case. So we are going to get, for these types of SN2 reactions, if the carbon is chiral, we are always going to get that that center should be inverted. So we'll get an inversion of configuration if this happens to be a chiral carbon. If it's not a chiral carbon, the nucleophile still attacks from the opposite side, but so we should get inversion of, if it's a chiral carbon, that chiral carbon. So the question is, I got a question in the chat. What is the antibonding orbital always on the opposite side of the atom bonded to the carbon? So for sigma bonds, yes. So if this was a, so what we're dealing with here is this carbon's an electrophilic carbon. We're breaking this bond here. The antibonding orbital is always going to be on the opposite side. Yes. Short answer to that is yes. Remember, pi orbitals are slightly different, but for the sigma orbitals like this, yes, the antibonding orbital is always going to be on the opposite side of that carbon there. Okay, so the energy diagram for this guy. So we've seen this before briefly. So this is a concerted process. So we start with our two products and we end with our two products. In this case, it's downhill. There's lots of ways, yeah, so we haven't really defined what X and nucleophile happen to be in this case. The key point is that this transition state is neither early or late because it doesn't resemble either. It's this trigonal bipyramidal structure. So the nucleophile bond is forming, the carbon leaving group bond is breaking. And around the equator, these three groups will be trigonal planar. So trigonal bipyramidal. So this transition state here isn't early or late, it's right in the middle. And so I got a question here at the bottom. What are some of the factors that might influence the activation energy in a substitution reaction? And I think it's, think about the alkyl halide, and let me move this little thing. My top hat always seems to, can't actually see what it says at the very, very bottom. But okay, so what are some of the things that could influence this activation energy? What we're gonna see is that really it's the structure of the alkyl halide which is gonna be the most important. There's gonna be some secondary factors which deal with the nucleophile itself or even the solvent of the reaction. But the most important factor by far is the structure of this alkyl halide, because the nucleophile has to attack that carbon from the opposite side. So that's the main thing that we're going to be looking at here. So is this carbon, the number of R groups, this is going to, as a number of R groups bonded to that carbon increase, the rate of a substitution reaction decreases. So what we're trying to say here is that if we've got carbon X, what's this carbon bonded to? If it's got R, 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 and you're some nucleophile, and you're trying to attack here, you've got all these big groups that are sort of blocking your approach. Whereas if you are a carbon and you've got X and you've got only one R group, this nucleophile coming in, it's going to be a whole lot easier because there isn't this steric sort of issue. So the more R groups you have, the steric interference is going to decrease the reactivity. So in the case of if you've got 3 R groups, it is so slow that you really don't see the reaction at all. So let's, and this basic sheet, this page, sorry, basically describes this. So it's really going to be interesting because where is my little laser? So as you add R groups, the steric bulk around this carbon increases. So tertiary carbons, tertiary alkyl halides, lots of steric bulk. Secondary, a little bit less. Primary, methyl. So substitution, these SN2 reactions are going to take place faster when there's less steric issues. So with methyl or primary alkyl halides, these undergo substitution reactions really easily. Whereas with tertiary, they do not undergo SN2 reactions at all because the nucleophile can't get in here to attack, or it's so slow that there's another class of substitution reaction that'll take place far faster. And with secondary, it's just, they undergo SN2 reactions, but the rate is reduced. So as the steric bulk increases, the rate decreases because the nucleophile has to attack from the opposite side. That's basically for substitution reaction. So methyl and primary are going to be fast. Secondary are going to be slower. Tertiary are going to be the slowest. Okay, one last question before we end class. So rank these basically based upon how fast they will undergo an SN2 reaction. And so what we need to do is look at the carbon which the bromine is bonded to and determine, is it primary, secondary, tertiary? And whichever one is the least bulky, has the less amount of steric interactions, will be the fastest, and those which have got the most steric interactions will be the slowest. Give a couple more seconds. What did everybody say? Okay, so A, B, and C. A, this carbon is a secondary one because there's one carbon, 2 carbons, secondary alkyl halide. This one here, B is a primary alkyl halide because there's only one carbon there. And C, this has got 1, 2, 3 carbons. So this is a tertiary. So primary should be the fastest, which would be B. Secondary would be the second fastest, which would be C. Wait, which would be the second fastest, which would be A. And then the C here has got 1, 2, 3, it's tertiary, so it should be the slowest. And that seems to be the majority of what everyone said. So that's good. Okay, so what we'll do on Thursday is wrap up SN1, or sorry, SN2, and then talk about SN1. There's another reaction which the tertiary is the fastest. So SN2 and SN1 will be completely complementary with one another when everything is said and done. I'll try to put together a really fast assignment, quick little assignment for the mechanism and energy diagram thing, but it probably won't get done until Thursday, but just keep that in mind. I think I've gone over my time a little bit. If you have any questions about today's lecture, just fire off an email, unless there's a question right now. Okay, if not, then I'll see everybody on Thursday and try to stay safe out there, given that it's a real mess in Manitoba. All right, so I'll see everybody on Thursday. Have a good bet. Now, let me see.